The multinomial distribution. Suppose on each trial of an experiment there are k possible outcomes. You've seen a special case of this in the case of Bernoulli trials, where there are two possible outcomes, success or failure. So the generalization that we'd like to permit here is for k to be 3 or more. And we'll assume that the trials are repeated independently of one another, a fixed number n times. And on each of these trials, there are k distinct types of outcomes. This is, for example, the case if I'm doing a poll. I'm asking polled individuals a question and they can respond A, B, C, or D. Let's suppose that the probabilities of these k different types of responses are P1, P2 up to Pk on each trial. In the multinomial distribution, we count the number of times each of the type 1 up to k occurs in n trials of the experiment. So I have a whole vector of values I'm trying to record the distribution of. I polled 100 individuals, 20 responded A, 40 responded B, 30 responded C, and 10 responded D. My vector of counts is 20, 40, 30, 10. Now that random vector is said to have a multinomial distribution by analogy to the binomial, which only has two categories of response, success or failure. Of course, the probability of these possible outcomes, P1, P2 up to Pk, those probabilities have to add to 1 since it covers all possibilities. So P1 plus P2 plus up to Pk, that sum is equal to 1. Similarly, if x1 is the number of responses of the first type and x2 the number of the second type, and so on, when I count the total number of responses of all types, x1 plus x2 up to xk, the total should be n, the number of trials. I suppose this means I don't really need to count all k types, because I could get xk by adding up the number of the first k minus 1 categories and subtracting that from n. For example, in the case of binomial, I counted the number of successes. I didn't bother recording the number of failures since I could get that by subtracting from n the number of trials. Here's an example. In a political poll, we ask 100 voters their voting intention for an upcoming election. And let's simplify the responses to 5 different categories. P stands for Progressive Conservative, L for Liberal, N for NDP, G for the Green Party, and U is undecided or don't care or something else. When I conducted this poll, I got the following results. X1 was 12, X2 was 15, X3 was 18, X4 was 15, and X5 was remarkably 40. There seem to be a lot of don't cares out there. Well, the random variables x1 up to x5 have a multinomial distribution. The probabilities P1 up to P5 are often estimated from data because they're not known a priori. Here's another example. Students are given marks that are letter grades, A, B, C, D, or F. In a class of 80 students, the number getting an A, let's call that x1, the number getting B is x2, and so on, down to F. This is a multinomial distribution as well. Little n is 80, there are 80 trials, and the number of possible categories is again 5, A, B, C, D, or F. Let's try and work out the joint probability function for a multinomial distribution. Let's go back to the political poll in which we had 100 randomly selected voters, and we interviewed them one at a time. And let's look at a particular sequence of responses. For example, pulgpl is the beginning of a very long word in which the first P tells me that the first response was Progressive Conservative, the second undecided, the third Liberal, the fourth Green, the fifth Green, the sixth again Progressive Conservative, and so on. What's the probability of that particular sequence of responses? Well, the probability of a P in the first place is P1. The probability of U, second, is P5, times P2, times P4, and so on. So I had a sequence of 100 letters there indicating the 5 possible responses of the 100 respondents. Then under it, you should see the product of 100 different probabilities, P1, P5, P2, P4, P4, P2, P5, and so on. But we can simplify that. Because P1 occurs x1 times, and P2 occurs x2 times, and so on P5 x5 times. So it simplifies to P1 to the power x1, P2 to the power x2, up to P5 to the power x5. But this isn't the only way I can obtain exactly x1 conservatives and x2 liberals, and so on. Any permutation of those same letters, any reordering of them, would be a different sequence with exactly the same probability, leading to the same counts. How many such sequences are there? How many repermutations of those letters can I find? This is the number of ways I can permute these 100 symbols, in which many of them are the same, which is n factorial divided by x1 factorial times x2 factorial up to xk factorial. That's the number of ways I can have a sequence with exactly the same counts. And each such sequence, we've discovered, has probability p1 x1 to the power x1, p2 to the power x2 up to p5 to the power x5. In other words, the probability of those counts is the product of those two things, n factorial divided by x1 factorial times x2 factorial up to xk factorial, times p1 to the x1, p2 to the x2 up to pk to the xk. In general, there are this many different outcomes, n factorial over x1 factorial up to xk factorial, different outcomes of the trials in which we have exactly the same counts, x1 of the first type, x2 of the second. And we've already established the probability of that. So this leads to the multinomial joint probability function. The probability of a specific set of counts, x1 up to xk, is given by n factorial divided by x1 factorial times x2 factorial up to xk factorial, p1 to the power x1, p2 to the power x2, pk to the power xk. In each case in that second term, we have the probability of a specific outcome raised to the power the number of such outcomes we counted, pi raised to the power xi. And that formula holds provided that the xi's are integers, less than or equal to n, and of course they add up to n, since the total over all possible outcomes should be n. We'll sometimes shorten the statement that this vector has a multinomial distribution to x1 up to xk is mult n p1 up to pk. And it's not hard to check that if you add over all possible values of x1 up to xk, the sum of those probabilities is 1. This is a consequence, in fact, of the multinomial identity that appears at the bottom of this slide. Here's a common example of the multinomial. Every person in a population has one of 4 different blood types, O, A, B, or AB. And in a large population, the fraction of these types, O, A, B, and AB, let's call those fractions P1, P2, P3, P4. In the United States, for example, the value of these PIs are about P1, 0.44, P2 is 0.42, P3 is 0.1, and P4 is 0.04. But interestingly, they differ considerably by country, because they're determined in part by ethnic origin. Suppose we select n persons at random from a population, and we count the numbers of types O, A, B, and AB, call them x1, x2, x3, x4. That joint distribution, we'll say, has the multinomial distribution with k equals 4. That's how many categories there are. What's the probability that in a sample of 10 people drawn from the US, no one has the blood type AB? Solution. We're looking for the probability that x4 is equal to 0. So we could take the joint probabilities, f of x1, x2, x3, x4, and add over all cases for which x4 is equal to 0. In other words, we add over x1, x2, x3, such that the sum of those integers is 10, while x4 is 0. And that's a rather complicated sum with many different terms. Fortunately, rather than add them all together, there is an easier solution, which applies whenever we're concerned about a single category for a multinomial distribution. Any one of the 10 individuals in our sample is either AB or not AB. If I count the number of AB individuals, considering that to be a success and any other blood type a failure, my count should have a binomial distribution with parameters 10 and 0.04. So the probability of 0 successes in 10 such trials is 10 choose 0, 0.04 to the power 0, 0.96 to the power 10, or 0.6648. Indeed, if I worked out the very large sum that you saw above, I'd end up, after quite a lot of summation, with the same answer. Here's another example. In search for a blood donor, individuals are sampled until 2 are found who have blood type AB. What's the probability that more than 50 people need to be sampled? And again, we'll assume that the PIs are given as P1 is 0.44, P2 is 0.42, P3 is 0.1, P4 is 0.4. Once again, it helps to consider AB individuals as successes and non-AB individuals as failures, because if we count the number of non-AB individuals sampled before we get the second AB, that random variable, y, has a negative binomial distribution. Total number of successes looked for is r equals 2. Probability of success, 0.04. And we're asked for the probability that y is greater than 48, or greater than or equal to 49. For example, if y is 49, that's the number of non-AB individuals sampled before the second AB, then there must have been at least 49 plus 2, or 51 individuals sampled. This random variable y has a negative binomial distribution. K is equal to 2, p is 0.4. And we're asked for the probability y is greater than or equal to 49. We could simply add together the values for the probability function from 49 to infinity. But this looks like a lot of work. Alternatively, y is greater than or equal to 49 if and only if, after we sampled the first 50 individuals, we either have 0 or 1 AB individuals. So the probability y is greater than or equal to 49 is, using binomial probabilities, 50 choose 0, 0.96 to the power 50, that's the probability of no AB individuals in the first 50, plus the probability of exactly 1, 50 choose 1, 0.04, 0.96 to the 49, and that's about 0.4005. Here's another example, a problem from insurance. For example, in automobile insurance, individuals are classified into various classes depending on characteristics such as their age and their driving experience. Let's suppose there are classes A, B, C, and D. And the probabilities of those four categories are 0.1, 0.4, 0.3, and 0.2 respectively. Class A consists of the least risky policyholders. They're charged the least, $1,000 in annual premium. Similarly, those in category B are charged $1,800, in C, $2,600, and in D, the riskiest, are charged $4,000. The question is, what's the expected total premium to be paid by 1,000 policyholders drawn at random? Solution. We noted earlier that each of the components of a multinomial, xi, has a binomial distribution. The parameters are n and pi. In this case, n is 1,000. This tells us what the expected value of xi is. It's n times pi. If we have 1,000 policyholders, there are x1 type A, x2 type B, x3 type C, and x4 type D. So the total premium that we receive is $1,000 times x1 plus $1,800 times x2 plus $2,600 times x3 plus $4,000 times x4. What's the expected total premium? It's the expected value of this quantity, which is 1,000 times the expected value of x1, that's n times p1, plus 1,800 times the expected value of x2, that's n times p2, and so on. We've already seen what p1, p2, p3, and so on are. And if we simplify the algebra a little bit, this is 1,010 to the 6th times p1 plus 1.8 p2 plus 2.6 p3 plus 4 times p4, or 2.4 million. Here's a review problem. Normally, individuals are being tested for a type of bacterial infection. They're either infected, let's call that I, with a certain probability, 0.02, or not infected, that's Ni, with probability 0.9. Otherwise, the test is indeterminate, so their status is unknown, let's call that U. That has probability 0.08, and in this case, additional tests have to be conducted. We'd like an expression for the probability that at least 20 people in a group of 80 are either I for infected or U for unknown. If a test administered in a high school gave 20 individuals like that, what might you conclude? Solution. We're given the three probabilities. P of I is 0.02, P of Ni 0.9, and P of U is 0.08. For a given individual, the probability that the outcome is either I or U, let's call this a success for the moment, is P of I plus P of U, which is 0.02 plus 0.08, or 0.1. So that if we define y, the number of individuals in a group of 80 that are either I or U, then y has a binomial distribution with parameters n equals 80 and p equals 0.1. We're asked for the probability y is greater than or equal to 20. We can get this by simply adding up the probabilities using the binomial probability function, the sum from 20 to 80. 80 choose x, 0.1 to the power x, 0.9 to the power 80 minus x. Numerically, this is somewhere around 10 to the minus 4. So what do we conclude if these tests discovered 20 people in a group of 80 that are either I or U? Because this probability is very small, we might conclude that the trials are not independent of one another, or those probabilities, P of I and P of U, are greater than quoted above. A lack of independence would occur, for example, if the infection were contagious and that there was a local outbreak of the disease or the infection.